You likely don't recognize this man, but if you're watching this video, you're probably aware of his problem, because this is Monty Hall. Monty is now more famous for this problem than for his 50-year career as a game show host, actor, and television personality. If you know about Monty's problem, you probably also know of the many videos on YouTube about it. I hope to provide additional insight on how outcomes change as you study the many variations you can consider. Let's first discuss the original Monty Hall problem and some simple variations. Even if you're familiar with this, I hope this initial discussion will provide better insight. I was familiar with the Monty Hall problem for many decades before I found myself trying to explain it to others, and realizing the usual explanations left me thinking, but why is that? In the traditional problem, there are 3 doors, one has a prize behind it. The contestant is asked to pick a door. The host then chooses one of the losing doors the contestant did not pick and asks if the contestant wants to change to the other unopened door. The question is whether the contestant is more likely to win by switching. If you're familiar with this scenario, you will know switching is better. In fact, the chances of winning are doubled by switching. Explanations usually involve noting that the host provides the contestant with additional information by picking a losing door. While this is indeed true, it was never clear to me why this doubled the chances of winning. With 3 doors, it's not hard to check all possible scenarios. Without any loss in generality, we can assume the first door is the winning one. If the contestant picks this winning door, the host can pick either losing door. In either case, it is better to stay with the original door. If the contestant picks the second door, the host can select only the third one. Here it is better to switch. Finally, if the contestant picks the third door, the host is constrained to choose the second one, and switching is better again. So, staying doesn't change the contestant's 1 in 3 odds, but switching improves the winning odds to 2 in 3. You may have noted that the odds sum to 1. That's not a coincidence. When Jane picked the first door, its chance of winning was fixed at 1 in 3. Monty's 1/3 chance of winning must then go to the only unchosen door, i.e., the leftmost door. That door will then have a 2 in 3 chance of winning since we know that someone must win if all the doors are chosen. When Jane is the only contestant, choosing to switch doors puts her in John's place. So, switching gives a 2/3 chance of winning while staying remains a 1/3 chance of winning. One can also consider the likelihood of each outcome. Again, without a lack of generality, I assume the first door is the winning door. If the contestant picks this first door, the host can pick door number 2 or number 3. If the host picks number 2 and the contestant switches, she must switch to door number 3. This will happen 1/6 of the time. Likewise, if the host picks number 3 and the contestant switches, she must switch to door number 2. This will also happen 1/6 of the time. In both cases, the contestant will lose by switching. If the contestant picks door number 2, the host is forced to choose door number 3. If the contestant switches, she will pick door number 1 and win the prize. This happens 1/3 of the time. The scenario is nearly identical if the contestant picks door number 3. The host must pick number 2, and the contestant will win by switching to door number 1. This happens 1/3 of the time. Totaling everything up, we see that switching means the contestant will win 2/3 of the time as opposed to 1/3 of the time when she doesn't switch. Let's explore the case in which the host is unaware of what door the contestant picked but knows the prize's location. Regardless of the contestant's choice, the host can pick door number 2 or number 3. If the contestant picks door number 1, the situation is exactly as before, and switching means that the contestant will lose 1/3 of the time. If the contestant chooses door number 2, the host can still choose door number 2 or number 3 in this scenario. If the host also picks door number 2, the contestant can switch to either door number 1 or number 3. In 1 in 12 cases, the contestant will switch to the winning door, and in 1 in 12 cases, she will switch to the losing door. If the host chooses door number 3, the contestant will switch to the winning door. This happens, on average, 1 in 6 times. The situation is nearly identical if the contestant initially picks the third door. Summing all the winning and losing outcomes establishes that, in this case, the odds of winning increase from 33% to 50% if the contestant switches. Considering additional contestants and viewing the host as a contestant is useful when extending this problem to other scenarios. Let's consider the traditional case from this viewpoint. again take 3 doors, but we don't know which hides the prize. One of them does, and it's equally likely that the prize is behind each door. Thus, each door has a 1/3 chance of hiding the prize. Let's say the first contestant, Jane, picks the rightmost door. Jane has a 1 in 3 chance of winning. Monty, our host, picks the middle door. But we know Monty will pick a losing door, so the likelihood of it hiding the prize is 0. The second contestant, John, is then given the leftmost door. But we know someone must win because all the doors have been selected. Then, where does Monty's 1/3 chance of winning go? When Jane picked the first door, its chance of winning was fixed at 1 in 3. Monty's 1/3 chance of winning must then go to the only unchosen door, i.e., the leftmost door. That door will then have a 2 in 3 chance of winning since we know that someone must win if all the doors are chosen. When Jane is the only contestant, choosing to switch doors puts her in John's place. So, switching gives a 2/3 chance of winning while staying remains 1/3. Let's now explore the case of 4 doors. One might first think that the chances of winning by switching are again 1 minus the initial chance of winning, i.e., 3/4. However, considering the case when there are dozens of doors, it should be clear that while the chances of winning by switching continue to increase, it does so at a lower and lower rate. Consider 3 contestants, Jane, John, and Emily, such that all the doors eventually get picked, and someone must win. It should be clear that if Monty picks first and 3 doors remain, each will have a 1/3 chance of winning instead of the 1/4 chance before Monty picks. Now consider the case in which Jane chooses first and picks door number 1, giving her a 25% chance of winning. Monty then picks door number 2, identifying it as a losing door. The 25% chance of Monty winning must then be distributed among the contestants. Jane still has a 1/4 chance of winning, which means Monty's winnings must be distributed evenly between John's and Emily's chances. Thus, their chances each increase by 1/8 to 3/8. In this scenario, Jane can increase her chances of winning to 3/8 by switching with either John or Emily. Now consider the case in which Monty picks after Jane and John. Jane and John each have a 1/4 chance of winning. When Monty identifies one of the losing doors, his chances of winning must go to Emily, who will then have a 1/2 chance of winning. Should Jane switch with John, her chances won't change. However, if she switches with Emily, her chances will double to 50%. Thus, if she knows Emily picked after Monty, she should switch with Emily, who has been given information about what door not to choose. If Jane does not know who picked after Monty, then if she switches, it's equally likely she will do so with John or Emily. Jane's chances of winning will be the average of John and Emily's, or 3 in 8. With a better understanding of the process, exploring the case with an arbitrary number of doors is easy. Let's, for example, take 9 doors, where each door has a 1 in 9 chance of hiding the prize. Jane picks a door which I label door number 1. Monty then picks a losing door which I label as door number 2. This door now has a 0 chance of winning. If 7 more contestants were allowed to each pick the remaining doors, someone would have to win, and the chances would need to sum to 1. Knowing the remaining doors are all equally likely to hide the prize, one can distribute the original chances of Monty's door winning to the remaining doors. Someone picking one of these doors now has an 8 in 63 chance of winning. Jane's chances of winning if she decides not to switch are generally, of course, 1 in D, which denotes the number of doors. When she switches, Jane's chances are the original probability each door contained the prize, plus the original probability of Monty's door spread out over the remaining doors. Since there is D-2 remaining doors, this additional probability is 1 divided by D times D-2, which can be rewritten as D-1 divided by D times D-2. The ratio of these probabilities is then D-1 divided by D-2. Note that when D equals 3, we get the classic result that says Jane's chances of winning are doubled by switching. As D gets large, this ratio approaches 1. Thus, while it's always better to switch, as the number of doors grows, the increased odds decrease. Let us now consider what happens if Monty picks another losing door so that the chances of that door hiding the prize become 0. This door's chances of winning must then be distributed evenly across the remaining unchosen doors, so the total probability of there being a prize behind one of the doors is 1. Thus, the 8 in 63 odds must be split 6 ways and add a 4 in 198 chance of winning to the remaining doors. The total probability for these doors then is 4 in 27. We had the switch to win probability when Monty picks one door as d-1 divided by d times d-2. To that we add the additional probability of d-1 divided by d times d-2 times d-3. This is the probability the door hid the prize before Monty selected it divided by the d-3 remaining doors. The second term can be written as 1 minus 1 over d-3, which can then be written as d-2 divided by d-3. Cancelling the d-2, the resulting expression is d-1 divided by d times d-3. We could have also obtained this directly by investigating the case in which Monty immediately picks two doors after Jane chooses. This is a good check because it shouldn't matter if Monty picks both doors at once or one after the other. Continuing as before, if Monty selects another door, its probability of hiding the prize gets distributed over the remaining doors. Doing the math, the remaining doors have an 8 in 45 chance of being the winning door. In general, we add the win probability of this newly identified losing door to the remaining unchosen doors. After some simplifications, we see that the pattern continues, and the win probability of the remaining doors is d-1 divided by d times d-4. If Monty selects a fourth door, the win probability of the remaining doors becomes 2 in 9, or generally d-1 divided by d times d-5. The pattern should then be clear. If Monty picks h doors after Jane picks a door, the chances of winning by switching are d-1 divided by d times d-h-1. As Monty keeps selecting losing doors, the win probability of the remaining doors becomes 8 in 27, then 4 in 9, and finally 8 in 9. If there were two contestants, 9 doors, and Monty opens 7 losing doors, one of the contestants must win. The contestant picking before Monty has a 1 in 9 chance of winning, so the one choosing after Monty must win 8 out of 9 times. So far, we have an equation that generates the switch to win probability as a function of the total number of doors, and the number of doors the host opens. This assumes the contestant only picks one door, and the 1 in the equation conspicuously looks like it could be the number of doors the contestant picks. Let's explore if that is indeed the case. Again, take as an example the case of 9 doors. If Jane is allowed to pick 2 doors, her chance of winning is 2 in 9. In general, if C is the number of doors she can choose, and D is again the total number of doors, her initial chances of winning are C divided by D. If Monty picks a losing door, the win probability of that door goes to 0, with the 1 in 9 chance of it hiding the prize divided evenly over the remaining 6 doors. In this example, the remaining doors have a 7 in 54 chance of containing the prize. Generally, each door's chances increase by 1 divided by d times d minus c minus 1. If Jane switches all her initially chosen doors to new doors, her chance of winning will increase by c times this amount. Simplifying, this becomes c divided by d times d minus c divided by d minus c minus 1. If Monty picks another losing door, the 1 in this equation becomes 2. Generally, if Monty picks h doors, the final expression is c divided by d times d minus c divided by d minus c minus h. If we define lowercase c to be c divided by d and lowercase h to be h divided by d, we are left with an equation in terms of ratios of the doors picked by Jane and those selected by Monty to the total number of doors. We started with this equation for the win probability for the cases in which Jane picks one door, and thought the 1 in the equation might reflect Jane's picks. Exploring the situation further, we found it was not quite that simple. If c is 1, we do indeed reproduce the top equation, but there was an extra c in the numerator hidden. This final equation, in terms of lowercase c and h, which are the ratios of the number of doors picked by Jane and Monty to the total number of doors, illustrates a key point about scaling, something we in science call dimensional analysis. If we double the number of doors, double the number of doors Jane can select and switch, and double the number of doors Monty picks, the probability is unchanged. Thus, if instead of the original situation with 3 doors and Jane and Monty picking 1 each, we have 6 doors with Jane and Monty picking 2 each, the probability of winning by switching is the same. This is all assuming there is only one prize. One can study cases with multiple awards, but then we need to define more clearly what constitutes winning. Does Jane win if she finds one prize, or must she find both? At this point, it is always better to switch if Monty picks unchosen losing doors. The initial probability of these losing doors gets distributed over the unchosen ones. So, can we construct scenarios where switching is worse? To do so, we must relax the constraints on the doors Monty can select. If he can only pick unchosen doors, switching is always better. But what if he is allowed to pick from the losing doors Jane has chosen? Again, let's look at the case with 9 doors but allow Jane to pick 3 doors, so her initial chances of winning are 33%. Monty also chooses 3 losing doors, but 2 of those doors must be from the 3 Jane initially selected. The probability that those 2 doors hid the prize becomes 0, but the sum must remain 1, so how are the remaining probabilities adjusted? Jane has done nothing, so her chances of winning are still 1 in 3. Thus, the 1 door Monty did not identify as a loser must now have a 1 in 3 chance of winning. In other words, the probability of the losing doors Jane initially selected is transferred to the one she selected that could still be the winner. Monty also selects one of the remaining losing doors, transferring its chances of winning to the remaining unselected doors. Distributing the 1 in 9 probability over these remaining 5 doors means they each have a 2 in 15 chance of hiding the prize. If Jane can switch her 1 remaining door, her chances of winning will drop from 33% to 13%. Clearly, it is better in this situation for her to stick with the door she initially picked. As Monty continues to select doors, the chances of winning by switching to one of these doors increase to 1 in 6, then 2 in 9, 1 in 3, and finally 2 in 3. Let's explore how equations can represent this behavior. We still have the stay to win probability as the number of doors Jane picks, C, divided by the number of total doors, D. The switch to win probability needs more careful consideration. If Monty does not choose any losing doors Jane has not already selected, the probability those doors are winners remains 1 in 9. If H sub C is the number of Jane's doors selected by Monty, then this base probability is generally C minus H sub C divided by D. In this case, the door's likelihood of winning remains 1 in 9. If Monty had just picked one of Jane's doors, switching both doors would mean she would have a 2 in 9 chance of winning. As a reminder, we are only considering the case in which Jane switches all the doors she initially selected. One can also consider the case where the number of doors she switches is not equal to the number of doors initially selected. I'll leave that as an exercise for the viewer. As before, when Monty selects a door Jane has not chosen, its win probability goes to 0 and is distributed evenly among the remaining unselected doors. If we denote the number of doors Monty selects that Jane did not select as H sub D, the win probability increases by an amount C minus H sub C times H sub D, divided by D times D minus H sub D minus C. This simplifies to D minus C times C minus H sub C, all divided by D times D minus H sub D minus C. Taking the ratio of these probabilities results in C replacing D in the last equation. We can again introduce lowercase variables that are their uppercase counterparts divided by the total number of doors. The equation then reduces to this. The question is now, is this ratio greater than, equal to, or less than 1? If it's greater than 1, Jane should switch. Switching does not change the win probability if it's equal to 1, but Jane should stay with her original selection if it's less than 1. Rearranging this last expression, we find that switching depends on the ratio of the number of Jane's doors Monty picks to the number of unselected doors he picks. Jane should not switch doors if this ratio exceeds lowercase c over 1 minus lowercase c. Note that the right-hand side of this expression is always positive, so Jane should always switch if Monty does not select any over her doors. Jane should stay with her original selection if Monty picks no unselected doors. Otherwise, whether switching is better depends on the situation. Graphing this partitions the space of parameters governing the situation into 2 regions. If the situation puts Jane inside the blue region, she should switch. Otherwise, she should stay with her original selection.